So very good evening class. So we're going to continue with chapter 2. As you all know, chapter 2 is a very long chapter. So after this, a few slides, some of it we have already covered how to actually solve in tutorial. So we're going to glance through them a bit quite fast. So if you have any questions, so please do stop and ask. If you don't understand anything, please do stop and ask, because we don't have the luxury of time here. So we have some of it is relatively simple and we have already done before, so there's no point for me to again explain unless if you don't understand. I just actually send you the link for all the codes which we did for chapter 2. I think you might have received a class notification just now. So it's I shared all the codes, labeled it. I have made separate codes if you visit. If you visit that link, you can see that I've already separated the codes. So what I want you all to do is please download the codes. I will try to upload whatever code that I try, but please do not depend on my code alone. There are times when we go through, we are not going to do every single example here that we see in the slide. Some of it or most of it you have to do on your own. Of course, in the beginning part I am sharing all the codes with you, but later on I expect that I won't be sharing every single code. There's some code that you have to try by yourself. Is that okay? So let's proceed with this continue yesterday. So this night class that we're doing is somehow or others helping in the sense that even though I'll be away for a few days, actually quite a number of days, by constantly having this replacement class actually helps to cover up a lot. So it's better to do consistently throughout the semester. If we finish early, then we can rest at the end of the semester. Rather than rushing everything towards the end, I think this is way better. So can those at the back hear me? So yesterday we actually stopped at case issue. Now we have already done the MPLAB simulation during our tutorial. So if you notice that the PIC 18 instructions can be written either in uppercase or lowercase, it doesn't matter. So this is what I mentioned earlier about the MPSN allows the user to include this INC file to provide registers definition for the specific processor. I didn't mention why we want to include it. Now some of you during tutorial you might have realized that when you click build you have error. Then it's mentioned that the FSR1 register, for example, in our, did I do with you? Can't remember which section, or I have not done it. It's actually another section. So when they compile, the instruction is actually LFSR, FSR1, hex 120 is actually the question from your test 1. We're actually doing simulation for the other section. So, but then it came out error. It mentioned that FSR1 is undefined. So when you look at the instructions, it's correct. LFSR, FSR1, comma, hex 120, it's correct. But why is it giving error telling it's undefined? Because the student forgot to put this include. When you forgot to put this include file, remember the special function registers is undefined. Yeah, hash include.
Instagram.
The hash include. Must have the hash include, otherwise your special function register will be undefined. So all special function registers and bits are defined in uppercase, so take note of this. Bits means like F and W. Remember I always told you put it in uppercase. The convention followed in the text says using lowercase for instructions and directives and using uppercase for special function registers. So that's what we have been doing all this while. This is just for your information. Now, earlier I mentioned about the big Endian and little Endian thing. So big Endian is actually stores the most significant bit at the lowest address and stores the least significant byte in the highest address. This is the reverse of what we are doing now. We are actually following this little Endian method, stores the most significant byte of the number at the highest address and stores the least significant byte of the number in the lowest address. Now this is what MPLAB is actually doing. If you see this instruction, let's say move move LW hex 20. The instruction for this, the opcode for this instruction is hex 0E20. 0E20 is actually 16-bit, right? Double byte. If you see this 20 is actually the lower byte. Lower byte is actually stored at the lower address, which means this hex 20 actually is actually stored at 001A, and the higher byte, the lower byte actually stored at 001A, and the higher byte, which is 0E, it is stored at 001B. So that means the lower byte gets stored in the lower address, higher byte gets stored in the higher address. Do you all follow? So, and the MPLAB also is following this convention. So we are actually following the little Endian method. Any questions so far? So programs for simple arithmetic operation. Now these are some of the quite simple and straightforward adding instructions. So I won't be demonstrating, I'll be going through them quite fast. I hope that you all can try this in MPLAB. So the question here says that write a program that adds. Now what we're going to do now, what is actually this example is for, is to show how you are going to solve this particular task. Now we have done something similar in tutorial, but we, as I mentioned earlier, we actually use graphics aid. We actually draw and then we solve it. So the same thing here. Write a program that adds 3 numbers stored in data registers hex 20, hex 30 and hex 40. So now it's actually 3. 1, 2, 3. Adding 3 bytes together. And place the sum in data register at hex 50. So the solution would be, you will actually break into step. If you ask me, I prefer to actually draw it. So the first step, what you're going to do, you're going to load the content of the first file register, which is hex 20, into working register, and then you're going to add the number stored at hex 30 and the number in the working register. You're going to add, and also the number inside working register, add WF, and the answer you're going to leave it in the working register because you want to add to the next one, right? So then you're going to add the number stored at hex 40 with the number, with the content inside working register, and again you're going to leave the sum also in working register, so that the final answer you can move WF to hex 50, which is the result. It's quite straightforward, right? So this is how we actually write. The first instruction, you move the content of hex 20 into working register, and then you add these two content, the answer is stored in working register. And then you add the third one, the answer also is stored in working register, the final one, you store the final answer in hex 50. Now this one, again, what you can practice is, you can use data directives to replace this address. Is it okay? Any question up to this point? Anything you don't understand? It's quite simple. Now, we have a program to add two 24-bit numbers stored at hex 10 to hex 12. And hex 30 to hex 15, and leave the sum at hex 20 and hex 22. So maybe I have to draw it. Just forgot to bring my marker. See if I can use my pen. This is going to be the ugliest drawing, but bear with me. I need to upgrade myself to using stylus pen. Looks like Optimus Prime, right? Okay, it says write a program to add two 24-bit numbers. Maybe next time I need to get the pad with the pad. I'm actually humiliating myself in front of the camera. So add two 24-bit numbers means, 24-bit numbers means, oh sorry, it's actually 3. Because 24-bit means it's 8, 8, 8. So it's actually 3. I'm just drawing so that you get the idea. sort at hex 10 to hex 12, which means here will be here will be hex 10, here will be kindergarten scribbling. And hex 12. And then this one would be, this is following little Indian method. That means the lower address, the smaller address will be on the right hand side. The higher address will be here. So likewise with this will be 20. I'm thinking twice to publish this video. Okay, so this is add two 24-bit numbers. Yes.
Is it 13, 14, 15? It's stored at 13 box.
Yes, it's 13, 14, 15. Let's see, we got eraser.
Control Z.
Yes, it's nicer.
Leave the hex.
We are I'm constantly trying to improve myself from compound Y to compound. So this one will be
X13.
It's the ugliest 13. Okay, the next laptop I'm going to get will be the touch screen. Okay, you get the idea with the ugly handwriting. And of course, the down there is hex 20, 21, 22. Okay. So here, take note that last time we mentioned that we have three add instruction, right? The first one is add WF. The second one is add literal to working register, and the third one is add WFC. And I did mention that the add WFC is used when you're adding more than a single byte. Now here's the case where we add more than a single byte. This is already 3 bytes, right? So for the first part, this one you solve like a normal, you use add WF. That means the first, the content of the first file register you move to working register. You move this to working register. And then you add these two, right? And then you can store the answer here at hex 20. The next one, you see, when you add these two, there is a possibility of having a carry here, right? It's a possibility of having carry. So what you should do for the subsequent byte is you should move this to working register. But then you add WFC, you add with carry. So as you can see, you can separate this one segment. This is the second segment. So this is for the first byte. If you see first byte, just moves the hex line to working register, and then you just add without add WFC. So you may ask, sir, what happens if we put add WFC? In this case, nothing will happen now because initially the content of C is 0. So we'll add 0, so it doesn't make any difference. And then you move the answer to hex 20. So you're done for the first byte. Now when you add, there's a possibility of having a carry here. So you move the first one, hex 11, into working register, and then you add WFC with hex 14. Then, but you move WFC. If there is a carry, it will add 1. If there is no carry, it will just add 0. So just use a WFC so that when you get a carry, you'll get the right answer. The rest is the same. Now the same thing also applies here. When you add these two values, there's a possibility of having a carry here as well, right? So for the second one also, you must use add WFC. That's the only difference. Other than that, the rest is same, and this is ugly. It's okay. Understand? Any questions? Any questions? Yes.
So will the carry flag does the value itself change?
You mean when you add a C? Yes, it will increase by 1.
It will increase by 1.
Yeah.
That means our answer is, let's say like 70, you increase it to 70.
Yes. Because carry is 1 word, so it's supposed to add 1 to it. So if there's a carry, it will increase by 1. If there's no carry, then it will add 0, which means there's no increment. Is there any other questions? Okay. Now this example, right, a program to subtract 5 from memory location hex 10 to hex 13. Actually we have done this in tutorial question, right? Did we? Yes, we have done this. So this is peanuts. We have already done this before. We subtract the hex 5 from file register. So what we do, we actually load and then we use sub WF because this is F minus W, right? This instruction is F minus the W square. And you store the answer at F. So that's why you can see that the destination is F. We have seen this, we have already done this in tutorial. Any question on this? Can we skip to the next one? Now this one is now, just now we did addition, multiple byte addition. Now you can do multiple byte subtraction. Write a program that subtracts the numbers stored at hex 20 to 23 from the numbers stored at hex 10 to 13. So which one minus which one? So we can have 3. So which address is going to be up? This one or this one? Yes. Hex 10. Oh, sorry. Again, I made a mistake. Because this is hex 10 to 13 is 4 byte. So hex 10 will be actually on top. So until hex 13 and the bottom one will be hex 20 until 23. Then you get the answer here. This will be hex 30 until hex 33. Hope the teacher doesn't hurt your eyes. Whoever's going to watch the video is going to end up laughing. The kind of teacher teaching this. Anyway. So here for the first part, we are definitely going to use F minus W, so it's going to be sub W F, right? Because F minus W. So that means in this case you actually have to load hex 20 into working register. So you have to move F. And then you subtract working register from file register. And then you can store the answer in working register and move the working register to hex 30. Now whenever you're subtracting here, there's a possibility of you borrowing something from here. Right, from the previous one. Borrow means you are minusing from this value by 1. So there's a possibility of you borrowing. So when the second one, when you want to subtract, it's the same thing. You move the second digit, this one, into working register, and then you subtract, but with B. So it will be F minus W minus B. Minus B if the lower byte borrowed anything means minus the borrowed. If you don't have, you want minus 1. Is it okay? So is it necessary for the first byte to use sub WFB? It's not required because this is the first, it is the lowest digit, and before this there is no any digit to borrow from this particular digit. So this one has a possibility of having borrow. How about this one? Yes, and same goes with this one. So when you actually do in terms of coding, see the first one, it doesn't have sub WFB. The second one has WFB if you have borrow means. And the third and the fourth. You have to consider borrow because there is a possibility of having borrow. That's why you have to consider. Is it okay? Now all these examples, the best way is for you to actually do an MPLAB and try to learn. Any questions? Now we have come to the chapter of, we have covered more than a single byte addition. It's quite relatively easy compared to single byte. You just have to use the WFC or sub WFB. So it's not a complex kind of thing, it's relatively quite straightforward. Now the next one we're going to go is, now sometimes when we want to perform, before this, all the addition that we have performed or the example that I've shown you, the content of the, or the value which we are adding or subtracting, usually it is in hex, right? Hex value. But sometimes we want to perform decimal calculation. That means we want to calculate or solve the arithmetic operation using decimal number. But this decimal number will be represented in hex. So we are actually going to use binary coded decimal, BCD addition, to actually do this. So Tiban, can you pause and change?
Yeah.